So this is the back of G10. We're just going to finish G10 real quick and then we'll do G11. So what we had done in number 2 was we had done stoichiometry to find the theoretical yield of NO2. But one thing I want to emphasize is whenever you use this 22.4 liters per mole, that's only true at STP. That is at STP. Is our lab ever going to be at STP? No. The pressure might be close to standard pressure, but the temperature in the lab is always going to be above standard temperature. So once you find your theoretical yield at STP, when you do your stoichiometry, you're going to have to make some adjustments to see what that would be in the lab, okay? So for number 3, imagine that when you prepare to do scenario number 2 in the lab, you find that the conditions in the lab are not at STP as usual. The lab room's temperature is 22 degrees Celsius and the atmospheric pressure is 758 mmHg. Use the combined gas law to figure out what the theoretical yield would be in liters in the lab. So the combined gas law is P1 V1 over T1 equals P2 V2 over T2. Okay, so this will just allow us to make some adjustments from STP conditions to lab conditions. So I'm going to label this first part at STP, and I'm going to label the second part in the lab, okay? So there's not going to be too much adjusting going on, just some minor adjusting, okay? So at STP, notice that the pressure in the lab is in mmHg. So let's do the pressure at STP in mmHg, which is what, everyone? 760, okay? The volume at STP, the theoretical yield at STP is this 1.2 liters. And the temperature at STP is obviously 273, okay? So remember STP, if you ever forget, it's on here. 0 degrees Celsius, add 273 to get Kelvin. So that's at STP. Now let's do in the lab. In the lab, the pressure is a little lower. It's 758. The volume we don't know. We don't know what volume we should be expecting. The temperature in the lab, what's 273 plus 22? 295. There you go. So go ahead and solve for V2. It shouldn't be too far off, but the volume should be a little bigger because we're dropping the pressure and we're increasing the temperature. Dropping the pressure would cause the volume to get bigger. Increasing the temperature would also cause the volume to get bigger by a little bit. So volume should end up being a little larger. So you can cross multiply all this, cross multiply all that. Two. This 1.2 only has 2 sig figs. Yeah, always go with the lowest because we're just multiplying and dividing. So you should have gone 1.3, yeah. Right? Okay. V2 should be 1.3 liters. Okay, that makes sense. It's going to be a little bigger because the temperature is a little higher than STP and the pressure is a little lower than STP. Both of those would make it expand a little bit. So this is what you will do in the lab on Tuesday. You will have to adjust your stoichiometry answer from STP conditions to lab conditions, okay? So number 4, when we actually do the reaction in the lab at lab conditions, you're able to produce 0.41 liters of nitrogen dioxide. Calculate your percent yield. So this 0.41, is that actual or theoretical? Actual. So we have 0.41 liters. And then the theoretical yield, be sure you use the theoretical yield in the lab conditions, not at STP. In the lab conditions, it's 1.3. So this is kind of low. It's like 30%. Round it to 2 sig figs, so we get 32%. Okay, that's a bit low. Hopefully in the lab yours won't be that low, but a lot of people today in third period lab got maybe, I don't know, 60% yield. Gases are just tough. There's a lot of, they're very finicky, a lot of calculating where stuff could go wrong. It's also just hard to be sure you collect all the gas. There's always like, little leaks in all the plugs and stuff that we're using. So don't expect a percent yield that's as great as some of the percent yields we've gotten so far this year. Okay. Questions on gas stoichiometry? Just remember, whenever you do gas stoichiometry, it's at STP, then make your adjustments later. Okay. Last objective for unit G. G11. Just get out a piece of paper for G11. Man, we learned a lot of stuff in this unit. Remember we learned electronegativity? Doesn't that feel like a long time ago? That was part of this unit, yeah. Problem set Tuesday, test next Thursday. I posted that on Schoology yesterday. Next Thursday, yeah. Problem set will be due Tuesday. Practice test Wednesday, test Thursday. Mm-hmm. Okay, so the ideal gas law is what we talked about in the do now, okay? The ideal gas law works for any gas. It does not matter what the identity is, as long as the gas is behaving close to ideal, which means it's not under too much pressure or it's not too cold. But pretty much any gas we ever work with, we can consider it to be ideal behavior, okay? So the formula is P times V equals N times R times T. Okay, P stands for what, everyone? V stands for volume. Lowercase n stands for what? Moles. R is always the same number, 0.0821. Liters times atmospheres per mole Kelvin. And T is obviously temperature. Okay, so those are all being multiplied together. This is the only formula that we're using that involves moles. I know we've talked about moles being N before, but notice all these other ones don't involve moles. So this is a big hint, because one of the hardest parts on this test is knowing which formula to use because there's so many formulas. A big hint to know you need to use this formula is that you use this when the problem involves moles or grams. Use when the problem involves moles or grams. Because grams and moles, you can easily convert between grams and moles. So if they say anything about grams or they say anything about moles, this is the formula they're probably talking about. And just remember, please don't ask me what R is. R is a constant. It's always 0.0821. It's on your pink sheet. Okay, 0.0821. The units are liter atmospheres per mole Kelvin. That's not a formula, that's a unit. I know it's a complicated looking unit, but that's the unit. Let me pause for a second. Don't write this down, just listen. If you remember in the do now, I had you solve for R. R is equal to the pressure times the volume divided by the moles times the temperature when you solve for R. So if we rearrange this formula, we have R times N times T equaling to PV, or you can make that PV equals N RT. So what I had you do in the formula, in the do now, was I just rearranged this equation. Had you solve for R, you realized it was 0.0821, and you realized that it's always going to be 0.0821. No matter what you do, what type of adjustments you do to the other parts, it'll always be 0.081. So that's the ideal gas law constant. Okay, so that doesn't change. All right, example 1. We're only doing 2 examples here. What is the pressure of 0.500 moles of CO2 at 20.2 degrees Celsius with a volume of 2.5 liters? Okay. What is the pressure of 0.500 moles of CO2 at 20.2 degrees Celsius with a volume of 2.5 liters? So notice this is not like the other problems. In all the other problems, we were changing the temperature and seeing how the pressure changed, or we were changing the volume and seeing how the temperature changed, whatever. This is just a fixed amount of gas. Nothing is changing. It also mentions moles. Both of those are hints that you're going to use PV equals nRT. This is not a P1, P2 situation or a V1, V2 situation. It's a fixed amount of gas at a point in time. That's your hint that you're going to use PV equals nRT. And if it says anything about moles or grams, that's another hint. So spread the formula out. I really want to show you, do P times V equals N times R times T. Really spread those variables out. I want to show you what we plug in where. All right, so P is pressure. That's what we don't know, so you can put that in parentheses. V is volume. Write down 2.5 liters. I want you to keep your unit here. Keep your unit here. Equals, N is moles, 0.500 mol. Keep your unit. R is always the same thing, 0.0821 liter atmospheres per mole Kelvin. That's from your pink sheet. And the temperature in Kelvin, what's 20.2 plus 273? 293.2. Okay, keep your units. A lot of you I know don't like to write units, but when you take AP Chemistry, the AP graders want to see these units, and the units will also help you verify that you're on the right track. So if we solve for P and our units end up being ATM, we know we did all the right operations. So notice that moles here is in the numerator. Here it's in the denominator, so it cancels. Same with Kelvin. Kelvin's in the denominator here, but it's being multiplied by something that has it in the numerator here. Kelvin cancels, okay? So I'm going to simplify this. This side is going to be P times 2.5 liters. This side, 0.5 times 0.0821 times 293.2 should equal, I'll just tell you what it is. It's 12.036. And the units are liter atmospheres, L times ATM. So what do I do to both sides? Divide by 2.5, because we want to get P by itself. Divide by 2.5 liters, divide by 2.5 liters. Okay, what units are going to cancel out over here, everyone? Liters, okay? So that's the beauty of science. When you're working with units, you can always check the units, and that lets you know you did the math right. If the units work out right, you know you did the math right. That's basically what stoichiometry and dimensional analysis are. As long as you keep track of the units and you see that the units are doing the right thing that you need them to do, the numbers just kind of follow right along. So that should equal just 2 sig figs, 4.8 ATM. Okay. So there's no way to know if your answer makes sense or not. So just double check your math, double check your units. All right, one more example. So on your problem set, these will be towards the end of your problem set, but anytime it involves grams or moles, you know you use PV equals nRT. Okay, example 2, 685 liters of O2. This is a big sample of oxygen. Has a temperature of 621 Kelvin. If the pressure is 1,890 kPa, What is its mass? Okay, so when you see mass, you might look at your pink sheet and think, wait, nothing has mass. But can we, if we solve for moles, can we convert that to mass? Yes, okay. So when it involves mass, look for the one that has moles in it. So we have P times V equals N times R times T. Okay, this time we know the pressure, but what's the unit of the pressure this time? kPa. So you have a couple options. You can either convert it into ATM, or you guys see how there's another R? There's a second value for R that's liters kPa, not liters ATM, okay? So you can just use this value for R, okay? So 8.314, that's what we're going to use for R when the pressure is in kPa. So let's do that. Let's do it that way. So the pressure is 1890 kPa. The volume is 685 liters. The moles we don't know, so we're going to solve for moles. The R, again, we're using the value for R that has kPa, so it's 8.314 liters kPa per mole Kelvin. And then the temperature is already in Kelvin. That's nice. You don't have to convert it. So if you can write yourself a note that this is from your pink sheet, in case you see that later and don't know where it came from. All right, so go ahead and simplify each side and try to solve for N. And then once you get moles, then convert it to grams. Okay, so you do this times this. I'll show you my work up here. So when you multiply these, the units are kPa liters. And then N times, I got, and notice the Kelvin cancels over here, okay? So the Kelvins cancel because it's on the top and bottom, so this is liters kPa per mole. So to get N by itself, I would just divide both sides by that. So this side just simplifies to N. All that cancels. This side, it should simplify to 251, okay? What's kPa liters divided by liters kPa per mole? What are the units for the answer there? Just mole, right? kPa per liter, kPa liters cancels out. It's on the top and bottom. Moles is in the denominator of the denominator, so that means it's actually in the numerator, okay? So that's how you verify you did all your math right, but always pay attention that it's asking for the mass. So just do a quick conversion. The gas is O2. So just quickly convert 251 moles of O2 into grams of O2. Just do a quick mole to gram conversion. It's going to be pretty heavy. That's a lot of oxygen. So the molar mass is 32. So you should end up with 8,032 grams of oxygen. So just keep in mind when they ask for grams, you can solve for moles and then convert to grams. Or if they give you grams, you can convert to moles and plug it in for moles. Okay. So just remember that grams and moles are easily converted among each other. All right, that's the last for Unit G. So tomorrow we will do kind of a review worksheet for all of Unit G. I think tomorrow, yeah. Your problem set will be due Tuesday, and your test on Unit G will be next Thursday. So we learned a lot in this unit. All right, so for the rest of the period, you can work on your reading check, you can work on your pre-lab, you can wash your hands, you can do whatever you want.